Let's go ahead and take a look at the magnetic force.
The magnetic force F equals QV cross B. Forces again are vectors, and in this case it's a cross product. It's very similar to torque equals R cross F, in that the force is going to be perpendicular to both the velocity vector and the magnetic field. B is the magnetic field here. So the magnetic field, and we will talk about where magnetic fields come from, how they're created, how we can adjust them. But so the magnitude of this B field is just some number. V, of course, is in meters per second, and Q again is charge. So what do we need? Well, for a magnetic field to apply a force, we need a charged particle, not just a particle, not a particle with just mass. We need a charged particle. It needs to be moving, and it needs to be moving such that the velocity has a perpendicular component to the magnetic field. Okay, so let's go over some examples of kind of how this is going to work. And the right-hand rule is going to be this. There are lots of versions of it. You get to pick. The version I'm going to use most of the time is going to be, I'm going to put my thumb in the direction of the velocity. I'm going to put my fingers in the direction of the B field. And then my palm, really the normal vector to my palm, will tell me the direction of the force. Okay, and so let's go over some examples of that. So let's say that the magnetic field is up. Okay, the magnetic field is up, so the B field is up. And if I'm a charged particle, and I'm going to go this way, so I'm a charged particle, and my velocity is this way, what direction is the magnetic force? Okay, so point your thumb in the direction of the velocity. The thumb would be pointed to the right of the page. Point my fingers in the direction of the B field, so my fingers are pointing up the page. And then my palm, and again, it's the normal vector to my palm. So if you think about my palm's normal vector, right, my palm's normal vector is in the direction of the blue pen now, and that's out of the page. So the force of this thing would be out of the page. So in this scenario, the magnetic force would be out of the page. The magnetic force would be towards you guys. Okay, let's do a different scenario. Let's say the magnetic field were dots. And what dots mean, if you think of them as arrows, those are arrows that are coming at you. Right, so in this case, the magnetic field is coming at you, and let's say that the charged particle is going this way. So there's the direction of the velocity. It is charged, and this is the B field that's coming out of you. Okay, so follow the right-hand rule, and again, make sure you use your right hand. Put the thumb in the direction of the velocity, and your fingers need to be in the direction of the B field. This one's a little hard for me, but my fingers are coming at you. The thumb is pointing to the left, and so the magnetic force would be this way. Again, the palm's direction is normal to the palm. Thumb in the direction of the velocity, fingers in the direction of the B field, out of the page, and the palm, it would push this way. So the force would be up in this case. Okay, and again, you got to be able to do all of these. You can see that all three vectors in this case are perpendicular to each other. This would be up. Okay, let's do one more. Let's make the B field x's, and x's, that means that the B field is going into the page. Okay, let's make the charged particle go that way. So there's the velocity vector, it's charged, and there's some B field. Okay, point your thumb in the direction of the velocity, point your fingers in the direction of the B field. So my fingers are into the page, my thumb is up the page, and my palm is to the left. So the force would be left here. Okay, So you have to kind of get that right hand rule down. Again, this is the rule I use. Some people do kind of this. You can see that the thumb, the finger, and the other finger, this kind of gun thing, also gives that same idea. I definitely prefer, though, the velocities, considering you're usually just talking about kind of one charged particle, which you only have one thumb, so point that way. The fingers usually have multiple B fields, so use your fingers to do that, and then your palm tells you the force direction. Okay, so the right hand rule tells you that. Here's the strength of it, and now we need to talk about this next thing. Okay, let's use this guy as in our example. So you have this charged particle, and it's going this way, B field's this way, and it's going to be forced. So if the force is left, what direction is this going to go as soon as it enters the field? So it's going this way, and if it's going to be forced to the left, it's going to accelerate to this way, and so now it's going this way. Well, now what direction? See how instead of going straight up now, once it enters this field, it's going to be bent this way? But if the field is still into the board, and my thumb is now angled to the left, what direction is the force? Well, now it's this way. It's gonna bend me and bend me and bend me and bend me, and if my velocity gets bent, and now I'm actually pointed this way, what direction is the force? Well, now it's down. So see how I'm bending all the way around. I'm going like this, and I'm gonna get bent, 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 and look, I end up going in a circle. And so what happens is, you can think of this field as a bigger field, and it certainly does have to be big enough. If it wasn't big enough, then you could just get deflected and then you pass through. And once you're not in the field, then the field's not going to apply a force to you. But you get in this field and you get bent this way a little bit. But once your velocity gets bent that way, well, then the force, you see how the force is always inward? Well, then you get bent a little more. But then you get bent a little more, and all of a sudden then you get bent down, and you're going to end up going in this circle. Okay, so in reality, what happens to the magnetic? What does a magnetic force do? Okay, and the question will be, does it do any work? So remember, I want to remind you, this is they love to ask this as a multiple choice question. The work equals the change in kinetic energy. Do magnetic fields do work? Okay, and the answer is no work is being done. No work is being done because magnetic fields don't accelerate you. Why don't they accelerate you? Because the force is always perpendicular to the velocity. Okay, just think about the right-hand rule. The magnetic force is always perpendicular to the velocity. It's also always perpendicular to the B field, but it's perpendicular to the velocity such that if velocity is this way, the force is going to be this way, and then the velocity is going to be a different way. So you've bent the velocity this way, but now the force is this way, and then the velocity is this way, and then the force is that way. And hopefully you can understand that if that's the velocity every time, see how the velocity is just going to be bent around, and you end up going in a circle. Velocity is this way, force is in the middle. Velocity is this way, force is that way. Velocity is this way. Okay, the force vector, thus the acceleration caused by that force, is always inward, and you end up moving in this circular path. Okay, so what a magnetic force does is it really causes like a deflection. That's what they're going to say a lot. A deflection. A magnetic force deflects a moving charged particle once it enters the B field. Okay, and then we can do lots of things with this circle. Okay, we can say that, well, we know that F equals ma. The force acting on this thing, let's assume that the velocity and the B field are perpendicular. So the force acting on this thing is QVB. And we know that causes a circular motion, which you can replace centripetal acceleration by V squared over R. And then we can solve for R. So one of those powers of V are going to weigh. So let's solve for R. So R, the radius of this circular motion, is going to be mv all over qb. B. And hopefully that makes sense. It's an expected result. Think about it. How are we going to gauge the radius of our circle? Right? How big is this circle? Well, if the object is more massive and moving faster, then it'll be harder to bend it into a circle. So the radius should go up with an increased mass and increased velocity. And that makes sense. Both m and v are in the numerator, right? Increasing mass and increasing velocity should increase the radius. Well, what happens if you increase q and increase the b field? Well, then you decrease the radius, right? Increasing q and b isolate and make the b field stronger, so it's going to make the force bigger, and it's going to make then the circle tighter. So these are expected results, that r should be a function of all four things: the mass, the speed, the charge, and the b field. And the mass and the velocity should make the radius bigger with an increase of mass and velocity, and the q and the b's increase should make the radius smaller. Okay, so magnetic forces, qv cross b. This is our right-hand rule to tell you the direction of the force, or if you knew the direction of the force, you could figure out the direction of the b field required. Magnetic fields don't do any work because they don't change the kinetic energy. The force is always perpendicular to the velocity, so they cause deflections. And not only do they cause the deflections, as long as the field is big enough and wide enough, that'll actually cause the particle to go into a circle, and we know how circles work. Okay? So not only can we look at just one moving charge, but if, and again, you got to really think about this, that if we know the magnetic force is QVB, let's assume it's perpendicular again, I'm going to drop that cross product, okay? Then instead of looking at just a moving charge, this is really just some Q times some length over time times B, and Q per second is really just current. So we can really derive that we can also view it as the force is ILB. So instead of just one moving charge, what if we talked about a current carrying wire? Well, a current carrying wire is really a certain charge moving at a certain speed, but it makes more sense to talk about the current charge per second times the length. So this is some force that's going to be acting on this current carrying wire. So let's say this current carrying wire is in a magnetic field like this. So this X is some external magnetic field. What's the force on this current carrying wire of length L? And so what do? We point our thumb in the direction of the current. We put our fingers in the direction of the magnetic field. Those X's are then into the page. And so we would be going like this, and then the force on this would be up. Okay, so the force on this current carrying wire would be up. And sometimes, instead of talking about the force, we talk about the force per length. So this is the force, and we could say then the force per length is equal to IB or something like that. Okay. Okay, so we can talk about the force on a moving charge. We can talk about the force on a current carrying wire, because that's really what a current carrying wire is. I think that probably does it. We'll have to wait a little bit to talk about the creation of magnetic field and looking at Ampere's law, but this should get us a good start. I guess there's one more thing we want to talk about. Sometimes they'll bring up a mass spectrometer or a velocity selector. And what that happens is you want to get only a particular speed of particles, and you want to send it through something. So let's say we have this massive parallel plate capacitor. Okay, let's put positive charges here. And what do we know? Well, we know this has an E field then. We also know that the E field is this way, inside of this thing. So what would happen if we take a charge and we threw it that way? What's going to happen to this charged particle? Well, this charged particle will experience an E field, and it will go down towards this bottom plate. But what if we don't want it to go down to the bottom point? What if we want this charged particle moving at a certain speed v? What if we wanted to kind of just zoom through this thing? Well, then we're going to have some sort of force that balances. Again, the electric force, based on the electric field, is down. Again, the electric force we know is Q times E, and those are vectors, but the electric force is just in the direction of the electric field. But what about the magnetic force? Well, how would you have this balance? So then we need a magnetic force up. So if we have our electric forces down, we need the magnetic force up. Well, how do you get a magnetic force up? If you have a charged particle moving to the right. So our charged particle is moving to the right, and how do I need to point my fingers if I want my palm to go up? Well, we just kind of went over that on this top thing. That's the same thing as this. If I have a magnetic field into the page, so if I put my fingers into the page and my thumb is going to the right, my palm is up. So if I could produce an external magnetic field that had X's, then what would happen? I could arrange it that the magnetic force, which we know equals QVB, drop the cross product because I'm making sure they're perpendicular. And if I want these two forces to be equal, meaning I want to zoom, all you have to do then is make sure what? The charge doesn't matter. And if you want these charges to zoom through here unaffected, then all you need to make sure is that the velocity they're moving at is the ratio of E over B, where E is the magnitude of the electric field and B is the magnitude of that. If they're moving at this speed, they'll zoom through this unaffected. And all the other ones, all the ones that are going either too fast, if they're going too fast, they'll get pushed up by the magnetic force. And if they're moving too slow, there's not enough magnetic force and they'll hit the bottom plate. But only the perfect ones. And so this is a way you can set up, if you were only interested in the speed of certain things, you can go that way. And sometimes they'll even put, you know, like a sensor over here, so when they get through this magnetic field, maybe they're going to do this. Because once you get through this parallel plate, then if there are still X's over here, they do stuff like this as well. If there are still X's over here, when this thing leaves, remember it's going to get bent up. As soon as it leaves this thing, and then you can go that way. And then the radius, as we said earlier, QVB equals mv squared over r. And that this radius here is also then going to be dictated by the mass, because the radius here is mv over qb. And they do all sorts of stuff with this. Okay, so a mass spectrometer or a velocity selector, kind of the same deal here, is you're sending some charged particle through some parallel plate capacitor, which has an E field. The E field is down, positive plate to negative plate, which is going to have the electric force down. What direction does the B field need to be to have the magnetic force up? Because we want those two forces to balance, and if they're balanced, then we know that we're getting this velocity is unaffected. Okay, and then we also could figure out what the radius would be afterwards, kind of based on some of these principles. Okay, hopefully this helped to get you started on the magnetic force and the right-hand rule. You can start to tell directions of what needs to be what, and then we extended it from not only QVB but to ILB. And again, you're going to use this a lot when we start talking about circuits. We're always going to be talking about a current carrying wire rather than just a single moving charge.